During this session, the fourth session of this week, under dynamic inventory problems under risk, now we'll be discussing in detail the exact method of analysis under cost-based approach. In fact, this is very important, and when not only for the cost-based approach, even for the service level based approach, many a time we prefer the use of exact method of analysis. We have already explained what is the exact method of analysis and what is the approximate method of analysis. So this problem we will be dealing with during this session, and then we will be just introducing the concept of the service level based approach for the problem formulation and the solution. Now let us first talk about the exact method of analysis and why it is needed in many cases. Now let us first go back to our our discussions, or our say the description of the inventory control systems. So, and we have already in the past lecture session, in the previous lecture sessions, we have referred to three categories of problem: category 1, category 2, category 3. Category 1 means the variable demand, constant lead time, and then category 2 is the constant demand, variable lead time, and category 3 means the variable demand and variable lead time. Now in all these three categories of problems, it is assumed that the order quantity and reorder point for Q systems, obviously, or the order interval and the maximum inventory for the P systems are determined independently. We have referred to a number of say numerical problems, 4 specific numerical problems we have referred to, and if you say go through these numerical problems, you will find that we have been using the formula for determining Q, and another expressions or formula for determining the reorder point as far as the Q system is concerned, and same approach we follow for the P systems of inventory control. So you are familiar with all these the formulations. So that's why you are saying that the parameters we determine independently using approximate method. So as if there is no relation between order quantity and reorder point, or there is no relationship between order interval and the maximum inventory. Now we need to use the exact method for determining the parameters of an inventory control system simultaneously. That means what we have, that means one say we'll just formulate the problem in such a way that we have one cost equation, the relevant cost equation, and this cost equation we form in terms of both the decision variables. Okay, and that's why we say that we are determining in this particular method called exact method the parameters of an inventory control system simultaneously. In previous sections, the cost-based approach has been used to determine the parameters of a given inventory control system. However, an appropriate method, an approximate method using one separate cost equation for each parameter is used. Is it okay? So that's why it is called the approximate method. As in an actual system, the parameters are related, that's why they are dependent with each other. The exact method of analysis is required to be known. That means what we are saying, like say if suppose the order quantity is more, obviously you will find that the safety stock may be less, or if the order quantity is less, you can prove with the data that the safety stock will be more. And similarly for the P system related the parameters. Now, so if they are related, and when suppose this relationship is very strong, and we need to include this relationship in the formulation of the problem, obviously we must use the exact method of analysis. Longer the order period, the smaller need to be the safety stock during lead time period. Is it okay? So there are many examples, and these examples these examples are given in the textbooks, and so please refer to all these examples, so you will have a very clear idea of the dependency between the parameters in a given inventory control system. So for both P and P systems, the exact method can be used. So let us first talk about the exact method of analysis for the Q system. We can write down the total cost equation to determine the Q systems directly. That means to determine the working of the Q system essentially, because any any cost means wherever there is some activity and there is always a related cost. So what we can do, we can write down the total cost equation by enumerating the various cost components forming the total cost equation. This is very clear. So in terms of the average order period T in weeks, so here we are assuming that the time unit is week, that's why you have written weeks. It could be also in months or in years. The annual total cost equation TC is given by this expression. That means now what we have one total cost expression involving 4 specific components. So the first component is, that is 52 by T into CO. Okay, that means CO is the ordering cost per order, and 52 by T is basically the order the order cycle in or order period in weeks. And what we are assuming that in a year there are 52 weeks, that's why this term 52 comes. Now the next one is, this is the inventory carrying cost for the average inventory. Now here the TST by say 52 is your average inventory. So an average, that is the inventory, maximum inventory, and average inventory half of that. So this is essentially 2 into 52, that means 104. So S into T into CU into I. So I is the inventory carrying cost as a proportion of the average inventory which you hold. What is S? S is basically the annual demand in physical units, and CU is the unit price. Is it okay? So you refer to our the original expressions of EOQ where we have used these notations. Then the next one is, this is the safety stock. So what is the safety stock amount? That is W, and it is the carrying cost for the safety stock. And why do you keep safety stock? To avoid or to prevent the occurrence of stockouts. So obviously here what we are assuming, that in any order cycle there could be a stockout. So how many order cycles you have per year? That is 52 by T. And what is T? T is the order period in weeks. And what is K? K is essentially the fixed out of stock cost. This is initially we have assumed that the fixed cost remains or the out of stock cost remains fixed irrespective of the amount of shortages. So what is the probability of shortages? That is R plus W up to infinity Fy dy, assuming that the safety stock remains fixed. That means though even if you are keeping a safety stock, but you don't need to use it, okay, in any order cycle. So that is one particular situation. In certain cases you need to use certain portion of the safety stock in order to avoid, or in order to say that consider a situation where so the lead time demand is more than the average which you have assumed. So now what are these notations? That means ordering cost is given by this is the first term. The second term, that is this one, represents the carrying cost for the average demand. The third term, that is this one, that is the carrying cost per safety stock. W is the safety stock during lead time. So I is the inventory carrying cost, and the per unit the price is say CU. And what is the fourth term? Fourth term is the out of stock cost. So 52 by T into K into say R plus W to infinity Fy dy. So what is capital K? Fixed out of stock cost, that is our assumption, and R is the average demand during lead time. So we have used another notations, okay. Otherwise the same sort of expressions we have used in the previous case also. So to minimize the total cost simultaneously with respect to T and W, so what you need to do, you take the partial derivative of Tc with respect to T, as well as you take the partial the derivative of Tc with respect to W. So these are the two unknowns, or the two decision variables, and you take the partial derivatives, set them equal to 0, and then you have one expressions like this, one equation, and the second equation is this one, right? And then you follow the steps to get the solution. So after you follow all these steps, so you get solving these two simultaneous equations, what you get, ultimately you get these expressions. Is it okay? That means f of R plus W square equals to this one. This is the right hand expression in terms of the known parameters and some say parameters, as well as some the factors. So for example, like you have these expressions, and in order to get the values of say the order quantity as well as the safety stock, so you need to use this expression. So for example, weekly mean demand is 50 in units, physical units. The standard deviation is 5, that is also in physical units, and we are assuming that the demand is the normal distribution. Lead time is 3 weeks, assuming constant, and this one is actually that is the probability or the density function of R plus W. F R plus W is the normal distribution of demand for 3 weeks with mean equals to 150, and the standard deviation is obviously the 5 into 3. So what we are assuming, that the normal distribution, the mean demand, that means the time period mentioned as 1 week, whereas the lead time is 3 weeks. So obviously the normal distribution, the values that means are to be convoluted the 3 times, and when you convolute the normal distribution 3 times, what happens, that its parameter values, that means its the mean becomes n into 50. So n is 3 into 50, that is 150, and the standard deviation obviously it will be the 5 into root over n. So here n equals to 3, that's why to 5 into root over 3, that is 8.66. So if GW represents the ordinate looked up in normal distribution table, we have this solution, that means GW square equals to 8.66 square into these expressions, okay. With respect to the performance standard, say understock occurring once in 1,000 lead times. So what is the performance standards? That means it's a kind of it's a service level, that is 0.001. That means in one order cycle there is a possibility, out of 1000 order cycle there is a possibility of going out of stock. So that is just that we are referring to the event of stock out, but in that particular order cycle where the stock out situation has occurred, we are not mentioning the amount of stock out. So we are referring to a measure of service level which is the service per order cycles, SLC. So let the value of K be known as 168.1. Is it okay? We get the following expressions. Actually we get the value of GW square in terms of 1 minus F or plus W, okay, the cumulative distribution function. So following the iterative steps with assuming F R plus W equals to 1, because we have to use the iterative methods. In the first step, in the majority of the cases, this point is to be noted, no more than 3 iterations are needed. Is it okay? So you get you get a solution, and we find following these iterative steps, we find a value of W as 3.08. With W equal to 3.08, we find GW is 0.0035. That means you refer to the standard normal table, okay, and hence F R plus W is equals to this. That means it is to be divided by the standard deviation, that is 8.66, the 5 root 3. So this value is this one, okay, 0.00404, and the value of T is this one, that is 5.89 weeks. Hence the order quantity is 5.89 into 50, that is 2995. Safety stock is 3.08 into 8.66. Is it okay? So that is 26.7 approximated as 27, and the reorder point is 0.3 into 50 plus 17. It is 3 into 50 plus 17, that is say 150, that is 27. 3 into 50 plus 27 equals to 177. Okay, so this is the 3 time periods, that is the mean, it is reorder point, that means the demand, the average demand during lead time. So the lead time is 3 weeks, and each week the demand is the 50 units. That's why it is 3 into 50 plus 27. 27 is the safety stock. So 150 plus 27, that is 177. Now for the P system, if you opt for the exact method of analysis, so what is the procedure? So again what you need to do, that means you need to form the total cost equation in terms of the decision variables. So here the decision variables are order period and the safety stock. Is it right? So we minimize the total cost equation varying with both order period and the safety stock with regard to both the variables simultaneously. The total cost equation TC is given by TC equals to this one, that this is for the average one, okay, that is the ordering cost. This is the inventory carrying cost for the average demand, and this is R is basically the safety stock and the carrying cost for the safety stock, and this is essentially say the out of stock cost. And here what we have assumed that this expression is probability of going out of stock, and this is capital K, that means the fixed out of stock cost we have assumed. So all these details are here, that means Z bar is the average weekly demand, Q is the order quantity, LT is the demand, and this is essentially these notations we have used, that means it represents X by Q, okay, plus LT, that is this is the convolution of Fy FY, what is FY? FY is the PDF of demand distributions for 1 week period. That means this is the time period you need to consider, right? And what we have, that means the total cost equation can be modified when we introduce a number of changes with respect to stock out cost and the safety stock. This point already we have referred to. Like the first case is when out of stock cost is estimated per unit basis. Is it okay? So what is the notation we have used? When it is a fixed cost, we have a notation capital K. When the out of stock cost is estimated per unit basis, the notation is C subscript U. So what is the total cost expression? So the total cost expression is this one. This expression is the ordering cost. For the ordering cost, this expression is for so the inventory carrying cost for the average the demand, and this is the inventory. This is the safety stock carrying cost, and this is say the number of this expression is for the expected number of units short, and this is your the per unit out of stock cost, and this is basically the number of order cycles you have. So when safety stock is partially used and fixed out of stock cost, so this is another combination. So the first two terms in the total cost expression remain same, whereas the third term, what you use, that means in this particular case you need to determine the safety stock for the entire time period. Entire time period means the order interval plus the lead time. So that timing is small t, and so I into Cu is the inventory carrying cost, okay, that is the I is the proportion and Cu is actually the unit price. Now the how many units are in the you have in the safety stock. So sometimes you use the safety stock, or sometimes you do not use the safety stock. So what we are assuming that partially you are using the safety stock, is okay. So Z bar plus R, is it all right? So any value you use, that means it is greater than Z bar, but it must be within Z bar plus R. So that is the maximum amount you have during the order period as well as the lead time. So this is your actual the demand during the order period and the lead time, and the corresponding the PDF is obviously it is to be convoluted the t times. So that's why it is F superscript T y dy, and this is the part that means the fixed out of stock cost, the same expressions you have. This is the probability of going out of stock, and that is the fixed out of stock per cycle, and this is just one order cycle you have. With this one order cycle, and there are say the total number of order cycles per year. In the third case, when the safety stock is partially used, okay, we have already considered this case, that is you have to change this expression to this one. That means we are assuming that there is a variation in the safety stock, and out of stock cost is estimated per unit basis. So the per unit basis, that means this expression, that means this is the fourth term, and per unit basis means this is the expected number of units short. Is it okay? So and this is the number of order cycles, and this is the per unit out of stock cost. So you please go through all the four the components in this total cost equation, and if you have any doubts, obviously you can write to me, and definitely we'll be able to so the make you understand fully. So as far as possible, we have tried to make it as explicit as possible, and but the main point is that you must be able to write down the total cost expression in terms of the decision variables. So the first the condition is the given an inventory control system, you must be able to say identify the decision variables, and in order to identify these decision variables, that means you must be able to explain, or you must be able to describe the working of a given inventory control systems, and for which we always suggest that you better the present the inventory control systems, the given inventory control systems, with the help of the inventory profile. So once you draw the inventory profile, what the advantage you have? The advantage is that immediately you will come to know that what are the decision variables, and then at the next step you try to write down the total cost expression involving the 4 components, and all these involved in component in terms of these decision variables. Assuming a particular distribution for demand, say normal, we may find the solutions, values of order quantity and the safety stock. In majority of the cases, the solution in P system with exact method of analysis provides a better solution than with an approximate one. So this point is to be noted. That means for many items, you know that for what kinds of items or inventory items you prefer to use the P systems of inventory control, and usually for determining the parameter values of the P system, so better you use the the exact method of analysis, whereas for the Q system the solutions as obtained from approximate and exact methods may not have much difference. So this we can prove with the data, and when we take up numerical examples, so this point will be made more clear. So for the Q system you prefer to use approximate method, okay, whereas for the P systems you prefer to use exact method. So the P system is well suited for the items where central inventory control is desired. So this point also is to be understood properly later on when we discuss the supply chain, the concepts later on. So this point will be elaborated more specifically or more explicitly. Now till now what we have discussed, that is for problem formulation and solution, we have suggested the cost based approach. You also know that under certain conditions that cost based approach may not be reliable, and that's why it is to be avoided, particularly in a situation where the cost estimates are not reliable. So what is the alternative? Alternative we have mentioned, that is the service level based approach. Now let us, before I conclude this session, so let us define the service level once again, and let us get an expressions for the service level, okay. And we define service level for an item in a given time period. Now this is SLU, basically the service per units demanded. So the service level is nothing but the expected number of units shipped divided by the expected number of units demanded. Already we have defined. Now this is 1 minus expected number of units short divided by the expected number of units demanded. Now as soon as you use the term expected, it means the demand is known with risk. That means the demand has having a distribution, the probability distribution. That means the exact demand is not known. That's why we have used the term expected number of units shipped. So now we have used, that means 1 minus NR subscript R divided by SL bar, and this through manipulation what we do, this means 1 minus sigma L by SL bar to NR by sigma L, or it becomes 1 minus mu into FR. So what is mu? That means it is, we are referring to the Q system, and this is basically the lead time demand, SL bar. So average lead time demand is SL bar, and the standard deviation of the lead time demand is sigma L. Is it okay? So this we have assumed. So this is essentially sigma L by SL bar is nothing but the coefficient of variation, and that's why we have used this notation mu. And NR is the expected number of units short, okay, and if you divide it by sigma L, so it becomes FR. So FR is nothing but NR by sigma L. So NR is expected number of units short during lead time. That means we are bothering about only the lead time demand, okay, because we are referring to the Q systems of inventory control. There is a possibility of stock out only during the lead time for a Q systems of inventory control. Sigma L is the standard deviation of lead time demand, SL bar is the mean lead time, mean demand during lead time, and mu is coefficient of variation, that is sigma L by SL bar. Okay. So service level is defined for Q system here, and it is measured during lead time. And reorder level is we have used this notation small r, that is SL bar plus B, where B is equal to safety stock or the buffer stock. As has been observed, mu depends on distribution, not on reorder level, whereas FR depends on the reorder level. So this is the conclusion. So we have just started the discussing the procedures for say to be employed for problem formulation and solution in service based approach. So we consider problem formulation and solution for each of the three demand distribution in the standard form. The first one is the uniform distribution we will consider in the next lecture sessions, and we also consider the exponential distribution for demand, and we also consider the normal distribution. So the service level based approach and the exact method of analysis we will discuss in the next lecture sessions. Thank you.